Dear students, today we will talk regarding the double slit Fraunhofer diffraction. Fraunhofer diffraction pattern produced by two parallel slits. The width of slits is B and it is separated by the distance D. We will find the resultant distribution pattern at the point P is the product of the point P is the product of the single slit diffraction pattern and the interference produced by two point sources which is separated by the distance d. To calculate the diffraction pattern, we assume that the slit consists large number of equally spaced point sources and each point on the slit is a source of secondary wavelets. Let the point sources A1, A2, A3 and so on in single slit and B1, B2, B3 and so on in second slit. Assume the distance between the A1 and A2 is delta. So A1, A2 is equal to delta. If diffracted rays makes an angle theta with the normal of the plane of the slit, then the path difference between the disturbances reaching the point P from two consecutive points in a slit is delta sine theta. Okay, so this I already covered. The field produced by the first slit and second slit is uh, the single slit resultant amplitude, right? There we have found the A is equal to A0 sine alpha upon alpha. Here I just changed the notation. Instead of alpha I have written the beta. So from the first slit, field is E1A sine beta upon beta cos omega t minus beta. The field produced due to second slit E2A sine beta upon beta cos omega t minus beta minus phi. Phi is the phase difference and the value is 2 pi upon lambda into path difference d sine theta. You know the path difference d sine theta from this. Here you can the path difference between the two slits here is d sine theta. If you consider this single slit, it is b sine theta. If you consider like this, the distance between a1 and a2 is delta, so delta sine theta. But here we know from the single slit result the phi is equal to 2 pi upon lambda d sine theta. Phi is the phase differences between disturbances from two consecutive points on the slit. By corresponding the point, we imply that the A1, B1, A2, B2, A3, B3 which are separated by the distance d. Okay. For the resultant field at P, due to these sources, we will find the total field E1 plus E2. Okay, so E is equal to A sine beta upon beta cos omega t minus beta plus cos omega t minus beta minus phi. So this equation is nothing but the cos C plus cos D. So if you make a simplification from this equation, simplify this equation, you can get this equation. and this equation represents the interference of two waves. Each of amplitude has same amplitude, a sine beta upon beta, and differing in only by the phase, and it can be rewritten to a sine beta upon beta cos gamma cos omega t minus beta minus 5 by 2. Here the gamma is 5 by 2 is equal to pi upon lambda d sine theta. So this is the derivation cos c plus cos d, a sine beta upon beta, so 2 cos c plus d by 2 cos c minus d by 2. So you can write like this, and this term will cancel out, this and this will cancel out. So what is remaining here? Cos 5 by 2. Here omega t plus omega t is minus 2 beta and minus 5 by 2. So omega t by 2 means omega t by 2 means omega minus beta by 2 minus beta by 2 beta and minus 5 by 2. So you can write like this. So here cos 5 pi by 2 means here this 5 by 2 is gamma. So cos gamma 2 cos omega t minus beta minus 5 by 2 and a sine beta upon beta. So it is nothing but this is equation 2a sine beta upon beta cos gamma cos omega t minus beta minus 5 by 2, and gamma is equal to 5 by 2 is equal to pi upon lambda d sine theta. Okay. So from this equation you can write the intensity, and you know the intensity is the square of the amplitude. So I is equal to 4 I0, this term I0 sine square beta upon beta square cos square gamma. Hence the intensity distribution is given by I is equal to 4 I0 sine square beta upon beta square cos square gamma, where I0 sine square beta is the intensity distribution produced by one of the slits. Okay, and from the equation 6 we can easily say that the intensity distribution is the product of two terms, first term and second term. So first term, this term I0 sine square beta is the diffraction pattern produced by the single slit of the width b. This term related to diffraction pattern which is produced by the single slit of width b, and another term, this is interference pattern term which is produced by the 2-point sources separated by a distance d. So this term related to, this term is related to diffraction pattern, this term is related to interference pattern. Okay, if we didn't change the width, which one? This one, b, or here you can see here width b. If we did not change this width b, then first term sine square beta upon beta square will not change, no variation occur in this term. And one can only simply we can obtain Young's double slit interference fringe pattern. Okay. Next, for the position of maxima and minima here, so if you consider this equation 6, for the minima the intensity should be 0. So sine beta, if you put the pi, sine pi is 0. If you put the 2 pi, again is 0, 3 pi, again is 0. Or you can put gamma is equal to pi by 2, 3 pi by 2, 5 by 2, this will, intensity will 0. The corresponding angle of diffraction, the corresponding angle of diffraction would be given. So corresponding angle, we can write that the b sine theta is equal to m lambda. We can just write this equation in terms of lambda, b sine theta m lambda, and for this one we can write the d sine theta n plus 1/2 lambda. You know that in the diffraction the condition for minimum is m lambda, okay, and for the interference the condition is n plus 1/2 lambda. So here or you can just say that the corresponding angle of this one, it is this. So this one you have written in the terms of lambda. So pi 2 pi 3 pi, here is m lambda, here is n plus 1/2 lambda. And so this is regarding the minima. But if you talk regarding the maxima, interference maxima, when it is occurs, so when the gamma is 0, pi, 2 pi, maxima will occur. Interference maxima will occur. Or you can also say that the d sine theta 0, lambda, 2 lambda, 3 lambda occur. At that time interference maxima will occur. Okay, the actual position of the maxima will approximately occur at the above angles, okay, and which provided the variation of diffraction term is not that rapid. Variation of diffraction term is not so rapid, okay, this there is no variation in the diffraction term. Further, the maximum may not occur at all if theta corresponds to diffraction minimum. Again, you know the diffraction minimum condition is m lambda, and this is related to b sine theta. You have to remember for the diffraction it's a single slit, like slit width is b sine theta, the path difference is b sine theta is equal to m lambda for the diffraction minimum. Okay, these are usually called the missing order. For example, if we take the slit width is 0.0088 centimeter and the interference maxima are extremely weak because there is diffraction minimum, right? Diffraction minimum, there is interference maxima are extremely weak, around the theta is equal to 0.41 degree. So we can calculate this. If you calculate the theta, so theta is equal to lambda by b, sine inverse lambda by b. So if you know the lambda, if you know the wavelength, and if you know the width of the slit, this one, you can easily calculate the angle theta. So that is the first minima of diffraction term occurs. First minima diffraction term occurs. So you can see this in this image. So here image, the width of the slit is same 0.0088 in both the case. Here just the distance between the two slit, this one, distance between the two slit increased 0.35 to 0.07 centimeter. As you can see, the number of minima and maxima increased here. So here you can see here somewhere it is 0.41 degree angle, and the diffraction, first diffraction minima is very less, or you can say the interference maxima is very weak. Interference maxima here is somewhere is very weak. So here you can see this is the envelope This is the envelope. It is due to a single slit diffraction. This envelope, single slit diffraction, and whatever minima and whatever the inside is due to a double slit interference. This pattern, and you can see in this image. So here the D is 0. If you increase the D 0.016176 to 0.035 and 0.070, so number of minimas, maximas are increased. Here these are all the double slit diffraction pattern. Just increase the distance between the two slits, but at the same time width of the slit are same. You can understand this by when animated. So here uh, we just put this is two slit diffraction pattern. So if we put so only the interference, so this is two slit interference. If you put the diffraction, so this is the single slit diffraction envelope, and inside it diffraction and interference are both here. So this is due to a interference occur due to a two point source or two source, and this envelope is occur due to a single slit. Okay, further if we go here, next the next is n slit diffraction. Okay, what happened in the n slit diffraction? So in the n slit diffraction, the n number of slits are there, and the width is slit width is the same b, and each slit contain again n number of equally spaced point sources with the spacing delta. Thus the okay, and which is separated by the distance d. Thus the intensity at the arbitrary point P on the screen is essentially the sum of the n terms. So here the total intensity we can write E is equal to a sine beta upon beta cos omega t minus beta plus a sine beta upon beta cos omega t minus beta minus phi up to so on, and then the last term a sine beta upon beta cos omega t minus beta minus n minus 1 phi. Okay, here first term represent the amplitude produced by the first slit, second term is by the second slit, and so on. So we can rewrite this equation. We can taken out this term because this term is same, so this amplitude term we have taken out, and this is the equation, like series equation, like. So I will not derive this equation, I will put direct the solution of this equation. So in the solution a sine beta upon beta, and this term will added for the n slit diffraction pattern sine n gamma upon gamma cos omega t minus beta minus 1/2 n minus 1 phi. Okay, so again from this term you can write the intensity I is equal to I0 a sine square beta upon beta square sine square n gamma upon sine square gamma like this. Again, the gamma is 5 by 2 is equal to pi upon lambda d sine theta, that you already know. The corresponding intensity I is equal to I0 sine square beta upon beta square sine square gamma sine square n gamma upon sine square gamma. In this case also it is very clear cut. This is the product of two terms. First term, this first term is due to a diffraction pattern produced by a single slit, which is the width b, single slit of the width b, and the second term interference produced by n equally spaced point sources. Each of them are separated by the distance d. So here, if you put the n equal to 1, then this equation will be a single slit diffraction pattern. And if you put the n is equal to 2, it is again give the double slit diffraction pattern. Okay, so you can rewrite the equation for the single slit from this equation, double slit from this equation, or you can also get the right. If you put n is equal to 1, again get this equation, you can write 2, again get this equation for the double slit, and if you write to 1, you can get the equation for single slit. Here this is the equation for the n slit. Okay, the next topic is diffraction grating. The diffraction grating is an arrangement of which consists large number of lines or the equidistant slits is known as diffraction grating, and corresponding diffraction pattern is known as grating spectrum. Okay, since the exact position of the principal maxima in the diffraction is depends on the wavelength, and the principal maxima corresponding to different spectral lines, and these different spectral lines again correspond to different diffraction angle. From this diffraction angle you can find out the wavelength. Okay, so these grating spectra provide us an easily obtainable experimental setup to determination of the wavelength. So for this equation from the diffraction grating, delta theta m lambda upon n d cos theta m, m is mth order, first order spectra, second order spectra, mth order spectra, like this. This is delta theta and this is lambda wavelength, n number of lines per each, d distance between two slits or distance between slits, cos theta m. Okay, so this equation shows basically, we will not derive this equation, okay, but this equation shows narrow principal maxima if the narrow principal maxima, the sharper the spectral line, it means a large value of n is required. Okay, a good quality of grating is therefore required at least 15,000 lines per each, 15,000 slits per each for the good grating. And this for the commercial use, this grating is made up from the cellulose acetate. An appropriate strength solution of the cellulose acetate is poured on the rolled surface and allowed to dry to form a strong transparent thin film. And this thin film is detachable from the parent grating. And these impressions of grating are preserved by mounting the film between two glass sheets, and your grating is ready. So that's how grating is prepared. And nowadays also uh, gratings are also produced by holographically. So those gratings have a much larger number of lines per centimeters. Okay, there is a two type of diffraction grating. One is transmission grating and other is reflection grating. In the transmission grating you can see again the width is slit width, this one, and this is this distance. So you can see the envelope due to single slit diffraction, and this is due to slit interference. So zeroth order, first order, second order. The position of the principal maxima are given by this equation: d sine theta is equal to m lambda. And for the reflection grating, this is the incident and this is the reflection normal to the face. So d sine theta m means order, plus or minus sine theta I is for the incident. So d sine theta m plus or minus sine theta I is equal to m lambda. Okay, let's take one example for the diffraction grating. Consider a diffraction grating with 15,000 lines per inch. 15,000 lines per inch. So that if we use a white light source, the second and third order spectra overlap. So we need to show that second and third order spectra should be overlap if you use the white light source. Okay, so what is the first line is 15,000 lines per inch. So per inch, 1 inch means 2.54 centimeter. So distance between the two slits is 2.54, or distance between the slits, those slits are equally spaced. So 2.54 inch divided by 15,000 lines. So you will get that distance 1.69 into 10 raised to minus 4 centimeter. And let's assume that theta mv and theta mr represent the angle of diffraction for the mth order spectrum corresponding to the violet and red colors respectively, because we use the white source, right? So we have taken violet and red color, and we know the wavelength for the violet and red. Okay, assume that the wavelength of the violet and red colors is 400 nanometer and 700 nanometer. Okay, now what is in the question? Second and third order spectra overlap. So what we will do, we will find out the angle, we will find out the theta second order violet first. So theta second order violet sine inverse right? Second order multiply wavelength of violet color divide by the D, you will get the angle 28.2 degree. Similarly, we will do the second order for red color. Sine inverse second order multiply wavelength of the red color divide by D, you will get another angle. So second order violet, second order red. Now for the third order violet, sine inverse third order wavelength of the violet color divide by D, you will get some angle 45.23 degree. So now you can say that this angle is greater than the theta third order violet. That's why the second and third order spectra will overlap because of the theta 2r is greater than the theta 3 violet. Okay, if we do further a third order red, because we doing the second order violet, second order red, third order violet, and this is third order red, so it is greater than 1. That's why the third order spectrum for the red color will not be observed. Okay, so our condition is satisfied here. The second and third order spectra will overlap. We have already shown here. Okay, so next is resolving power of grating. The resolving power of grating refers to the power of distinguishing two nearly spectral lines, which is defined by lambda upon delta lambda. What is distinguishing two nearly spectral lines? Okay, if you see this, like distinguishing, this is lambda and this is lambda upon delta lambda. So this is actually not one, but this is actually two peak, 1 and 2. So distinguishing two nearly spectral lines, which is defined lambda and delta lambda. Lambda is wavelength and delta lambda is separation of two wavelength, which the grating can just resolve. Smaller the value of delta lambda, larger the resolving power. So Rayleigh criterion can also be used to define the limit of resolution. What is the Rayleigh criterion? So Rayleigh criterion states that two images are just resolvable when the center of the diffraction pattern of one is directly over the first minimum of diffraction pattern of the other. Okay, so what is the Rayleigh criteria? It states that the two images are just resolvable when the center of the diffraction pattern of one is directly over the first minimum of the diffraction pattern of other. Okay, so you can understand by this image the principal maxima corresponding to wavelength lambda plus delta lambda. The principal maxima corresponding to wavelength lambda plus delta lambda falls on first minima of the lambda. The two wavelengths lambda and lambda plus delta lambda are said to just resolved. Two wavelengths lambda and delta lambda are just resolved. So now the principal maxima, the principal maxima corresponds to the wavelength lambda plus delta lambda falls on the first minima of the wavelength lambda. So therefore the two wavelength lambda and lambda plus delta lambda are resolved. If this common diffraction angle is represented by the theta, and if we are looking the mth order spectrum, then the two wavelength lambda and delta lambda is just resolved if these following two equations are simultaneously satisfied. Okay, d sine theta m lambda plus delta lambda, d sine theta m lambda plus lambda by n. So if you compare this equation, so lambda by n is equal to delta lambda m delta lambda. So you can write like lambda upon delta lambda is equal to m into n. Okay, so we can use this equation to find out how many lines required to identify the sodium D1 and D2 lines. Okay, so the sodium has two lines D1 and D2, and you know, or we know, the delta lambda is 6 angstrom and wavelength of sodium also know 5.89 into 10 raised to minus 5. So these two things, 5.89 into 10 raised to minus 5 and 6 into 10 raised to minus 8, put in this equation, and this is for the first order. Here is 1, so you can find out the n number of lines for each is 1000 is required. To find out the sodium line D1 and D2, your minimum required line or slits is 1000. I hope you understood my lecture. So next is polarization. So here your diffraction topic is completed. Thank you.